So this is level 3 of power distribution network analysis. In this level, we're going to discuss a little bit more complex board, and this time we're going to discuss a motor controller. We're going to connect multiple motors, and there will be a couple of motor drivers plus few digital ICs as well. We'll have some regulators. So let's discuss the schematic and its layout first, then we'll move to power budget. Circuit starts from this input connector, you can see, and it is directly connected to 7805 regulator or LDO, right? Another thing is, from this same particular net, which is 12 volt in, it is going to a current protection where we are using a MOSFET, which is FDS 9435, and through sense register we are sensing the current flow through this MOSFET. And now that net, which is 12 volt, is connected to 3 different motor drivers and their H bridge, right? Because we wanted to rotate motors in both direction. And here the condition is also same as level 2. We're going to turn on motor one by one. We're not going to turn on motor together. So this is again a test board, and yeah, let's move to block diagram. Before that, I wanted to show you 12 volt line, how it is connected. So just hold control and click on this one. So as you can see, through bottom layer from this connector, it is going to this sense register, right? And from here it is connected to this one, right? And from here it is going to another sense register that is for motor driver, right? And from here it is connected to different motor drivers, right? Different MOSFETs of motor driver, those H bridges, right? So one is here, one is here, and one is here. These are the 3 things, and their output is connected to this 6-pin connector. Okay, so here we have to connect motors one by one, and I want to tell you current as well. So each motor can able to consume 3.5 amps of current. So accordingly, I have routed these traces, right? And same thing we'll mention on our power budget. Plus we'll simulate and feed all this information on PDN tool. So let's start with power budget first. So for power budget, let's open whiteboard. Okay, and as I mentioned, how current is flowing, it is coming from, so firstly, like we did for level 2, we'll start from block 1, okay? And block 1 will be a JST 2-pin connector. All right. And I'll keep mentioning net here, so there will be like no confusion. Okay, so this is plus 12 volt in. Now it is connected to a MOSFET, right? Because it is going to a sensor register, right, through MOSFET, and there we are sensing the current, and there we have set a electronic fault detection. So in case the current limit will exceed, it will turn off that MOSFET, right? So I've told you the MOSFET part number, which is FDS 9438, right? 9435 something. Okay, this is 4. All right, so we are using a MOSFET here. Just mention that as well. Now this is going to a sense register, because sense register will also drop some amount of current, and that is 5 milliohm, but still it will consider everything. Now here the net will become in underscore 2 plus, okay, and here net will become plus 12 volt, right? Now in the same net, we're going to connect a 7805 LDO, okay, and that is powering some digital chips and some LEDs, okay. So this is connected to one LED through 1K. So I've already shared this project with you. In case of any doubt, let me know. I've already noted down these. So because the PDN analysis is going to take a lot of time, so let's do that quickly. And so here the voltage will be plus 5 volt. All right, and this is further connected to a dual mux, and again it is connected to some current sensor, because current sensor is also powering through 5 volt. All right, and yeah, these are all the 5 volt. Cool. Now we'll mention all the current here. So this is 1K 5 volt. What will the amount of current here? So here, let's use another color. I will be 5 milliamp, right? For dual mux, I'm going to use data sheet for this one. So let's see. This is our mux we are using. You can also use if you required in other circuit. This is like really good chip. Let's copy the manufacturer part number. I guess I've already opened. Okay, we have already opened that. And here you'll visit page number 4. And on this one, they have mentioned the supply current, which is 50 milliamps, right? So I'm just going to mention that as well on our sheet. So this will be 50 milliamps. For current sensor, let's see the part number. It's already opened, which is INA 300. And here the supply current is, as you can see, I've already highlighted. It's given on first page, which is 135 microohms. This is really good chip, and you can see the amount of current it is taking, and it covers almost all the protections you can read here, right? So let's mention that as well, 135 microamps. So this will be, we can, if you want, we can ignore that as well, but it is like 0.1 milliamps, right? Which is really small current, but let's consider for now, and later we'll see if we have to do that or not. Okay, for LDO, if you open the data sheet of 7805, the one we are using, its voltage drop is, I've already opened that. Okay, this for 7806, this for 7805. It is 2 volt for 1 amp and junction temperature 25 degrees Celsius. So 2 volt is a huge amount of voltage drop, and we'll see this, we'll add this total current and see what is the power loss here. But yeah, this is 2 volt drop. All right. Now we'll move to circuit block 2, which is connected to plus 12 volt here, right? So right now I haven't mentioned any voltage. What will be the voltage of this one, right? Because based on these drops, we have to increase this voltage if we want to maintain 12 volt. So, but before that, let's move to block 2. All right. So this will be our block 2. Okay. Now in block 2, the input voltage net is plus 12 volt. All right, which is coming through a MOSFET and current protection, right? And obviously a sensor resistor is also there. Now this thing is directly going to DRV 8701. DRV 8701, right? Plus here I am considering the MOSFET as well, plus MOSFET circuit, which is H bridge, right? And that is connected to our load, which is a motor, which can able to take 3.5 amount of current. And we have 3 similar circuits, right? DRV plus MOSFET plus load, which is 3.5 amps. Similarly here, DRV plus MOSFET plus load, which is 3.5 amps, right? And we're going to simulate these in a part of 3 network, because we're not going to power or we're not going to connect all the loads together, right? So this is a bit tricky, and I've already told you on level 2, so that would be a little bit easy for you. But yeah, if you haven't watched, just go there and watch that video first. All right. So now we'll do all the analysis, but before that we'll see, because most of the current, see, DRV is just a chip, right, which is providing a PWM on gate, but most of the voltage drop or most of the losses are through MOSFET, because across that we're going to connect our load, right? And that MOSFET will going to use an H-bridge MOSFET, which has 4 MOSFET integrated inside a single chip. It's a really good chip. I highly recommend to use it if you need any H-bridge in your circuit. Okay, let's move to that and see what is the RDS on that one. It's this one, right? And here, if you can see one thing. I wanted to rotate a motor, let's suppose clockwise, okay? And whenever you wanted to rotate a motor, there will be 2 MOSFETs connected in series. That means RDS on of 2 MOSFET will be in series. That will be the total voltage drop of this chip for clockwise and for counterclockwise as well. So here we'll see, this is the configuration that we are using. And on that, for 25 degrees Celsius, 8.7 amps can able to flow through these MOSFETs. And what is the RDS on? It is 30 milliohm multiplied by 2, right? So that is one thing I wanted to tell you. So that means there will be 60 milliohm for all of these. So for this also it will be 60, and for this also it will be 60 milliohm. All right. Now we'll see what is the voltage drop, and accordingly we'll see what should be the voltage on this one, right? So for 3.5 amps, what will the voltage drop across this? We'll just calculate it. So open calculator. 60 milliohms means 0.06 multiplied by 3.5, which is 0.21 volt, right? So 0.21 volt drop here, but at a time we're going to run one load. So that means at once this will be the only drop, right? So at input side, this side, we need 12.21 volt, all right, and 0.21 volt drop. Got it? Now let's move to circuit, this one. So here, as we have discussed, on this particular net, we need 12.21 volt at 3.5 amps. Got it? Now here we have to see what is the voltage drop across this one. Then we can able to calculate the voltage on in_2+ net, and similarly for this MOSFET. All right. So let's multiply it with 3.5. So 5 milliohm will be 0.05 multiplied by 3.5, which will be 0.175. Okay. So here the voltage drop will be 0.175 through this resistor. That means on this one the voltage will be 12.21. Let me know if I'm doing something incorrect on comment section, so I'll correct on another video. All right. So 21 plus 0.175, which will be 12.385. all right. So this voltage will be 12.385. Now we have another MOSFET which is FDS 9435. So on this one we have to see what is the RDS on here, and that again you can go through with this one, and here it's mentioned 80 milliohm for a particular configuration. All right. So this is 80 milliohm. Now I'm going to change color here. So what will be the voltage drop across this MOSFET? 80 milliohm multiplied by 3.5. Because all these things are connected in series, right? So current will be always same unless your source can able to provide that current. So this will be 80 means what, 0.8 multiply by 3.5, which is 2.8 volt drop. We'll add that on 12.385, so it will be 15.1 volt required here. So instead of 12 volt we need plus 15.8 volt. All right, and current and everything is clear here, right? So whatever the amount of current which is flowing on LDO, all right. So here voltage drop is 2 volt, but we are giving 15.8, but there will be huge losses on this one. So you have to dissipate that by stitching VRs, and you have to plan that thing. I hope, so again, when I'll select LDO and put these information in PDN tool, it will see what is the losses on 7805, and our copper can able to handle that loss or not. So it will, we can able to detect automatically. But yeah, let's calculate current for 7805. So which is the addition of these three currents, right? So that will be 5, 55 and 0.1, right? So it will be 55.1 milliamps. That is the amount of current and 15.8 volt, right? Dissipation you can calculate this current multiplied by 15.8 minus 5, right? So that will be your power dissipation through this LDO. All right. So these are all the things I wanted to discuss as a power budget of this particular circuit. Let's put these information on PDN tool and let's analyze the circuit together.